All right, class, let's work through the 12-2 homework, estimating limits algebraically. With the first couple of problems, they've given us the limit of 5x minus 10 as x approaches negative 3. And we could deal with the properties of limits. We're able to distribute the limit here through this expression. And so that becomes the limit of 5x minus the limit of 10. Well, I didn't write it underneath, but that's the limit as x approaches negative 3. And then you're able to factor out the 5. So that becomes 5 times the limit of x. And you'll remember from the teaching presentation, we like this because we can visualize this really easily. The limit of x, that's at the origin with a slope of 1 over 1. So if we have a positive line running through the origin, basically at a 1-to-1 slope, what happens when x approaches negative 3? Well, you get to visualize that you're going to the left, negative 3. When you hit negative 3, you're going to go down negative 3. And so as the limit of x, as x approaches negative 3, f of x approaches negative 3. We'll then multiply that times the coefficient on here, 5 times negative 3. Limit of equals 10, that's just a horizontal line through 10. So anywhere on the x-axis, it's going to equal this number. So that becomes negative 15 minus 10. So the limit of this expression is negative 25. What about the limit of this expression in number 3? Well, again, we're going to distribute the limit throughout the expression. We're going to factor out the coefficient when it's greater than 1. So this becomes the 7 times the limit of x squared minus 6 times the limit of x minus the limit of 3. Well, here, if you graph this, this is your standard parabolic equation. So as x approaches negative 1, f of x is going to approach 1. So that would become 7 times 1 minus 6 times negative 1. Here again, we have the same limit of x. What happens when x approaches negative 1? Well, f of x is going to approach negative 1. And so that's going to be minus 3. Do the math, and that adds up to 10. So the limit of this expression as x approaches negative 1 is 10. Move on to number 11. This one is not possible. We were using a direct substitution on these, and when we utilize direct substitution, that becomes 4 minus 4, which gives us a division by 0. So this is not going to be possible. It's not a possible way to solve this one using direct substitution. Here, using direct substitution, this is really just calculator work. It's just going to almost forget limits, just deal with your standard f of x. And what happens when f of x, what's f of 3? What's this expression when you have f of 3? Well, you plug it in and you end up getting 2. So the limit of this expression as x approaches 3 is 2. You could graph this and check it, and you'll get 2. So it's just a different way of solving that. All right, number 23. On this one, we can't do direct substitution. This is similar to a previous example, but we're actually going to carry it on. When we see we can't do direct substitution, what do we do then? Well, in this case, we're going to just factor this out into the product of binomials, and we'll see that x minus 4 cancel. And so our new limit, we could rewrite this whole expression as the limit of 2x plus 3 as x, or when x approaches 4. When we do that, let's just go back to direct substitution. Plug 4 in for x, and you get 11. The limit of this expression as x approaches 4 is 11. All right, for number 25, once again, not going to be able to do direct substitution, so let's factor this into the product of binomials. Hopefully you recognize this immediately as a difference of squares, so you can factor that into product of binomials. Here, the x minus 1s cancel. And once we get back to this point, x plus 5 over x minus 1, just use direct substitution, and you'll be able to estimate the limit as 3. The limit of this expression as x approaches 1 is 3. Let's move on to number 35. Now this one they were wanting us to we're going to have to use some the power properties, essentially. We see this expression as x approaches infinity. So clearly direct substitution is not going to work. Even if I try to reduce this, it's not going to work. We can't just plug infinity in. And so the way we want to think about it is, what if we work with the highest powered term, which in this case is going to be the x cubed. Let's keep the 7 with it just for illustrative purposes, but it's really a moot point, because 7x cubed we could rewrite as 7 times the limit of x cubed. And when we deal with this, we know because it's going towards infinity, if you graph this, you'll see what happens when x approaches positive infinity. Well, f of x is going to approach positive infinity. And you'll have to look back in your book, but I've written it down for you. Just remember when x approaches infinity, x to the n, it's going to approach infinity. But when we deal with the negative infinity, we've got a couple of different cases. In this case, take our highest powered term, and n is even, right? F of x is going to approach infinity. But if it's odd, it's going to approach negative infinity. That's when we're searching for x's towards negative infinity. Now, unfortunately, both of the homework examples I gave you approached infinity. It was just short-sightedness on my part, but hopefully you can remember these rules, that that's what's going to happen. So in this case, it is odd, and you would think, wow, that's negative infinity, but no, we're looking for it as when it approaches infinity, positive infinity. Let's look at 37. Again, this lengthy expression, but we're looking for x as it approaches infinity. So on the one hand, so you'll see this one is a little bit different than 35 because we're dealing with a rational function. So I believe this was example 6. And when we're dealing with a rational function moving towards infinity, we actually end up having to divide everything by the highest powered term, which in this case is x to the 5th. Now we don't divide by the coefficient, just the variable and the highest powered term. So you can see I divide everything by x to the 5th. Now the goal of this is to simplify this more complex expression down into something that's going to include a lot of zeros. So as I divide everything by x to the 5th, I begin to reduce these things down. 2x squared over x to the 5th is going to be 2 over x cubed. 7x over x to the 5th becomes 7 over x to the 4th. Now, how does that help me? I'll let you process the rest of those. Well, if I take the limit of 2 over x cubed, that's the limit of 2 times 1 over x cubed, which that's my reciprocal function, right? And so I factor out the 2, it'll be over here to my coefficient, so it's 2 times the limit of the reciprocal function. That's 0. As x approaches infinity, that's going to give me 0. This gives me 0. This gives me 0. In fact, just about everything gives me 0 except the limit of 3, because 3x fifth to the 5th divided by x to the 5th gives me 3. So the limit of 3 as x approaches infinity is 3. But anyway, that becomes 0 divided by 3, which is just 0. So the limit of this expression as x approaches infinity is 0. All right, let's look at our last problem, 59. They've given us a population boom in a little town, and they've modeled it by this algebraic expression, and they've asked us to calculate the rise in population in the number of years from, I believe it was 2006. And so here, this is calculator work. You can plug this into your calculator and just solve for P of 1, P of 2, and P of 3. And you will get these 3 values. If you use it properly in your calculator, my advice would be to use your parentheses well here. I would put a parentheses right outside the 36, and then parentheses here and here. And when you get to plus 13, do another set of parentheses, divide, open parentheses again outside the 3. And then you can use your back button and change the t from 1 to 2 to 3. And when you do that, you're going to get these values. And it looks really odd. When I first saw these, I thought, wait a minute, this is weird. Oh, and then I had to remind myself, this is a rise in population in the thousands. T is in the thousands. So that means that their P is going to be in thousands. So you got to multiply each one of these by 1,000. So these are the correct values for the rise in population from the year 2006. Well, what would be the rise in population by 2011? Well, if you just count up on your fingers real quick, right? You realize that 2011 is going to be 5 years from 2006. So now you're looking for P of 5. Hopefully you left this in your calculator for easy access. Just backtrack and replace the T with 5 and hit execute. You get 9.576, multiply that by 1,000, and it's going to be 9,576. C, what is the limit of the population growth? And so now we're looking for the limit as x approaches infinity. And as you solve accordingly, this is a rational function. So I'm going to divide everything by the highest powered term, which is t cubed. And that's going to reduce down to give, all of these are going to zero out. This is going to zero out because you're dealing with the reciprocal function. So we're just training our mind. We've looked at those parent functions earlier in the year. I talked a lot about them during the teaching presentation for 12.2. So you're going to have the limit of 36 over the limit of 3. Well, as x approaches infinity, that is 36 divided by 3, which is 12. But don't forget, this is in the thousands. So what's the population limit, or the limit of the population growth, I should say, is 12,000. Now, they ask you the question in D, why would we have a limit on population growth? And there's a variety of answers. This is a simple one that we could put forth. A city's physical boundaries may limit growth. They may just run out of room to build. And so there's a bunch of different answers you could probably put here, but that's a logical one. So guys, I hope this has been a good review of limits, estimating both graphically in 12.1 and algebraically in 12.2. There's a lot more to it. But we're out of time this school year, so make sure you send me your questions.